Thank you very much. It's a pleasure to be here. I've been coming to these things for a while now, and I guess this is the last one. But c'est la vie. So my title of my talk today is something like loop spaces, p-divisible groups, and character theory. So I want to start with something very classical. And at the end of the talk, I'm going to get this back to talking about topological field theories and talking about the thing that I ran my mini course on last week, for those of you who are here for that. But to start with, I want to think about the representation theory of finite groups. So let's suppose that G is a finite group. And I'll write rep G for its representation ring. You take complex representations of G, take isomorphism classes of them. They're a commutative monoid with respect to direct sum. And this is the group that you get by throwing in inverses. So one of the first basic theorems in the representation theory of finite groups is that representations are determined up to isomorphism by their characters. So there's a map that takes the representation ring of G to the collection of functions from G to the complex numbers. And that map takes a representation to its character, which I'll write as chi sub v. So chi sub v on an element G is the trace of the action of G on the vector space V. So the character of any representation is a conjugation-invariant function. And this map is close to being an isomorphism. It's an isomorphism if you tensor the left-hand side by the complex numbers. The representation ring of G tensored with C is just isomorphic to the ring of class functions, given by this construction of characters. So I'd like to first take this statement and make it look a little bit more like homotopy theory. So I'm going to use the letter K to denote complex K-theory. So there's a close relationship between the representation ring of a group G and the K-theory of the classifying space BG. A representation of G is just a local system on the classifying space BG. So any local system in particular you can regard as a vector bundle. It's a vector bundle, well, with some notion of flat sections. But this defines a map from the representation ring of G to the K-theory of BG. And this map is almost an isomorphism. Or more precisely, Atiyah and Siegel proved that you get the K-theory of BG by taking the representation ring of G and completing it with respect to a certain ideal, namely the augmentation ideal consisting of representations that have virtual dimension 0. So I'd like to perform an even more severe completion. So for this, let's suppose now that G is a finite P group. So P is going to be some prime number that I'm going to fix for the remainder of this lecture. So if P is a finite P group, if G is a finite P group, then you can also p-adically complete the representation ring of G. And that's a more severe procedure than completing with respect to the it's a more severe completion. So a consequence of the Atiyah-Siegel completion theorem is that this becomes an isomorphism after p-adic completion. Now we have to p-adically complete both sides. So let me write that as follows. The representation ring of G, if we p-adically complete that, well, that's just tensoring over the integers with the p-adic integers. And this is isomorphic. I'm going to write k hat of BG. So k hat means p-adically completed K-theory, different k hat than the one in the previous lecture. So this is just the cohomology theory that on finite spaces takes the usual K-theory of that finite complex and p-adically completes it.
So that's more drastic than that's not equal to K of BG when G is a P group?
It's not. For example, if G is a point, K of BG is Z, and K hat of BG is ZP. So,
except for that?
Probably except for that. I think that's right. So let's make use of this over here. So let's identify this. This is K hat of BG, tensored with the complex numbers. And here I'm going to think, well, I should be tensoring over ZP. So choose some embedding of the p-adic integers into the complex numbers. And that's what this left-hand side looks like. It has a name in terms of K-theory. And now what about the right-hand side? Well, I'm going to give this a slightly different name. This can be identified with the zeroth cohomology of the loop space of BG. So let T1 denote a torus of dimension 1. And here we have the loop space of BG. And we can take its cohomology with complex coefficients. So what does that look like? What does the loop space of BG look like? Well, it has one connected component for every conjugacy class of elements of G. And the connected components themselves are very simple. They just look themselves like classifying spaces of finite groups. So I'm writing here H0, but this space only has cohomology in degree 0, at least if we're using characteristic 0 coefficients. So the cohomology of this space is just functions from the set of conjugacy classes of G into the complex numbers. So what the main theorem of representation theory of finite groups is telling us in the case of a P group is something about the relationship between K-theory and ordinary cohomology. It's something that was a theme in the last lecture too. It's saying that the K-theory of a space has something to do with the cohomology of its loop space. So here we take the K-theory of a space and that's something that has some torsion in it potentially, but then we tensor it with the complex numbers to kill all the torsion. And that's supposed to be the cohomology with coefficients in C also of a space, but it's not the space you started with. Instead, it's its loop space. So there's a generalization of this theorem that was proved by Hopkins-Kuhn-Ravenel, where you replace p-adic K-theory by some other cohomology theory. But it's a statement of the same flavor. I'll get to it in a minute. It's a statement of the flavor that if you take some cohomology theory and you apply it to a space, and then you ask, what does that look like rationally, say after you tensor with the complex numbers? Well, it looks like the rational cohomology, or maybe I should say the complex cohomology, of another space. Not the space you started with, but one that's obtained by a simple procedure. So to set up the context for this theorem, I need to introduce a definition for you. So here's a definition. A Morava.
One question.
Yes.
I mean, the last talk it was suggested that, I mean, not just for BGs, but for much more, say, for general manifolds, we have some relation between K-theory and the equivalent quantity loop space.
Mm-hmm.
So, I mean, do you think that this generalizes to
well,
more than BG?
there's some. I mean, that story is certainly closely related to this one. I mean, this one is a purely algebraic story. It has no analysis in it. And I could imagine that you could tell a story that involved both of these ingredients simultaneously. But I will not. So a Morava E-theory is a cohomology theory E for E-theory, satisfying three conditions. So one is, well, this is going to be something that's probably not familiar to if you're not a stable homotopy theorist. But E is represented, or can be represented, by a commutative ring spectrum. So let me just say a brief word about that. So we're talking about some kind of cohomology theory, and maybe we imagine that there's some kind of representing cocycles for this cohomology theory. So if our cohomology theory was ordinary cohomology, we could represent cohomology classes by cochains or cocycles. Or if we were on a manifold, by differential forms. If our cohomology theory was K-theory, we can represent cohomology classes by vector bundles. So imagine whatever this cohomology theory E is, there's some analogous notion of cocycle, and we want E to be represented by a ring spectrum, which means we have some procedure for multiplying the cocycles. And moreover, that procedure should be commutative and associative, at least up to some homotopy coherent, in some homotopy coherent sense. So this in particular,
That is definitely homotopy commutative.
so this is strong. I don't want to write the word homotopy here. I want
Stronger.
it's the stronger. It's E infinity, but I don't want to use E infinity because there's already an E on the board. But
It's the infinity.
it's an E infinity ring spectrum, yeah. Okay, so it's a multiplicative cohomology theory, and the multiplication on cohomology classes is commutative and associative, and that's true for a good reason. That's what I want to say here. Okay, so that's nice. Condition 2 is going to be some...
K-theory is an example, right?
K-theory is an example, yeah. K-theory is going to be an example of one of these, or p-adically completed K-theory is. So here's condition 2. So I'm going to tell you what the E cohomology groups of a point look like. Well, the cohomology of a point is going to look like a power series ring over the p-adic integers on n minus 1 parameters. So n is some integer, and these parameters are in degree 0. And then you have an additional invertible parameter in degree 2. And finally, let me say something about the E cohomology of a very simple space. Not quite as simple as a point, but take the classifying space of the group Z mod P. The E cohomology of this space should be a free module. The cohomology of this space is going to be a module just from the fact that E is a ring spectrum. That's always going to be a module over the cohomology groups of a point. But I want to say this is a free module of rank p to the n. So
Same n.
yes, same n. So if you're not a stable homotopy theorist, this is probably not a familiar definition to you, and I will sympathize if this seems sort of random. But, well, let me mention, so for any p and n, any prime number p and any integer n greater than 0, there exists a Morava E-theory. There exists a cohomology theory that satisfies these conditions up here, where for this value of p and n. So this is traditionally written. The traditional notation is to write E sub n, where you indicate n in the notation and you don't indicate p. So p is something that's fixed for all time throughout this lecture, some prime number. And
there's some formal construction that produces it.
There's some formal construction which produces it. And moreover, it's essentially unique. It's not quite unique, but it's unique up to some kind of Galois twisting. So if I, instead of taking zp, which is the Witt vectors of the finite field with p elements, if I put the algebraic closure of that finite field in, then this cohomology theory would actually be uniquely determined. But you should think of these things, really there's just one for every p and n. And a canonical example is one that we've already met on that other board over there. If n is equal to 1, p-adically completed K-theory. is a Morava E-theory. Because, well, there's a nice way to multiply cohomology classes. You tensor vector bundles together. This is just saying that the cohomology of a point should look like ZP in degree 0. And there should be some kind of twofold periodicity. That's the Bott periodicity theorem.
And there are no V's.
There are no V's in that case. And condition 3 says if you look at the p-adic K-theory of BZ mod P, that should be a free module of rank P. And indeed, what is it? It's just you take the representation ring of Z mod P and you p-adically complete it. They're exactly P irreducible representations. So p-adically completed K-theory is an example of this. So I've defined this when n is greater than 0. By convention, you might extend this to the case where n is equal to 0. When n is equal to 0, what you're supposed to be talking about is rational cohomology. So or cohomology with coefficients in a field of characteristic 0. So in that case, fields of characteristic 0 don't detect whether you're talking about BZ mod P or a point. You'll get a free module of rank P to the 0th power. So ordinary cohomology with rational coefficients is an interesting cohomology theory. K-theory is an interesting cohomology theory. So what about these other ones? Well, they're probably not familiar to you because they don't, as of yet, have a geometric interpretation. There isn't a geometric description of what it means to have a cocycle for one of these cohomology theories. But if you're a stable homotopy theorist, these things are your bread and butter. These are very important in understanding the structure of the stable homotopy category. So you'll just have to believe me that these Morava E-theories are interesting because I'm going to talk about them from now on.
But it seems like it sort of changes dramatically as soon as n gets to 2 because the cohomology of the point is suddenly infinite dimensional.
The cohomology of a point, well, the cohomology of a point is a ring, and everything is a module over that ring. So, I mean, the cohomology of a point with coefficients in C is infinite dimensional if you view it as a vector space over Q. All right, so let's let E be one of these Morava E-theories. So a basic question that you can ask is, what is E of your favorite space? So let's suppose that your favorite space is BG, where G is a finite P group. Well, then the E cohomology of your favorite space was computed by Hopkins-Kuhn-Ravenel. Or, well, they didn't quite compute this. They computed what happens when you take this and you tensor it with the complex numbers. Let's say you tensor over the E cohomology of a point. And they got an answer that's an awful lot like this. So this is conjugation-invariant functions on the set of, well, let me write it as homs from Z to the n into G. So here you take a hom from Z to the n into G. That's just given by specifying n elements of G which all commute with each other. And you take conjugacy classes of such n tuples. And then you take the collection of all maps from that finite set into the complex numbers. And that's the answer that's prescribed by Hopkins-Kuhn-Ravenel. So that's exactly what this formula is saying in the case n is equal to 1. So let me write it a slightly different way. So let's introduce a notation for BG. Let's call it X. What we're saying is if you take the E cohomology of X and tensor it over the E cohomology of a point with the complex numbers, then what you're supposed to get is the ordinary cohomology. Well, I could write H0, but all the cohomology is going to be in degree 0 of the space of maps from an n torus into X with coefficients in C. And this is true not just when X is BG, but this is true for any p-finite space. So let me introduce that definition, because that's also going to play a role in this talk.
How is C an algebra over U of the point?
You choose an embedding, and then there's such an isomorphism. That's not the most canonical thing you can say, but the most canonical thing would require a digression. So, so let me define my term on that board up there. So we'll say that a space X, we'll say that it's p-finite if all homotopy groups pi I of x are finite p groups, and pi I of x vanishes for large values of I. So finitely many homotopy groups, and all the homotopy groups are required to be finite p groups. So it's something that's built out of Eilenberg-MacLane spaces for finite p groups. And the Hopkins-Kuhn-Ravenel theorem generalizes, you can take any space X, and which satisfies this condition, and the E-cohomology of X, at least its characteristic 0 reflection, is given by this formula. So what I would like to do in this talk...
This hypothesis doesn't necessarily, for non-simply connected examples, imply the action is nilpotent, I think.
It does imply the action is nilpotent.
It does?
And any... What's that?
Even at the prime 2?
Even at the prime 2. Remember, pi 1 is also a p group.
I know. The two adic units have elements of order 2, so I mean, there's an extra 2 torsion thing there. So okay, well,
there's an extra 2 torsion. Well, never mind. Exercise, and for any such thing, you don't have to worry about whatever you're worried about. All right, so what I would like to do in this lecture, let's see how much time I got. I got lots of time. So I would like to categorify this statement. So I'm going to tell you what I mean by that. So I would like to have this statement be a consequence of the existence of a category with some nice properties. So let me list those properties right now. So let E and X be as above, or as to the right. E is a Morava E-theory. X is a p-finite space. So let me state a hypothesis. So there exists a category which I'll call C. It's going to depend on X, so maybe I should write C of X, but never mind. And this category has a unit object, which I'll denote by 1. And this unit such that the following 3 things happen. So first, when we compute endomorphisms of the unit object, what we get is the E-cohomology of X. So homs in the category C from the unit object to itself should be the E-cohomology of X. Second, well, there should be some notion in this category of what it means to tensor with the complex numbers. So I'll write that as with a subscript C, meaning I take the unit object and then I tensor it with the complex numbers. And I could then compute the endomorphisms of that object. Well, maybe I should say C linear. C linear homs from this thing to itself. This should be identified with the cohomology of that mapping space. Take the n-fold free loop space of X and take its cohomology with complex coefficients. And finally, endomorphisms of the unit object are related to endomorphisms of the complexified unit object in the way that you would expect. Namely, you just take this and tensor it over the complex numbers to get this. So this tensor product will take place over E0 of a point. So surely you will accept that if there exists a category with these features, then we will have proved that we will have constructed an isomorphism as on the right-hand board. And the idea is this isomorphism is interesting, but having a category like this will be even more interesting.
Could you explain B? There's some
B?
writing up there I can't read it.
So,
what 1 sub C means.
So 1 sub C means you tensor 1 with the complex numbers. So maybe it will help if I say more about the kind of category I have in mind. So no one let me erase that. If it looks like I'm going to erase that board, someone say something. So let me give you a non-example. Let me tell you how not to construct a category with these properties. So, first a caveat I should mention is that when I say category, from now on, I really mean an infinity category. So this is going to be some kind of a homotopy theory. But if you're happy with those words, imagine that I'm inserting them. If you're not happy with them, you just ignore them.
Wait, can I momentarily not accept the thing that you said we all had to accept?
Which
is that if we had this, we would get such an isomorphism?
Yeah.
I mean, your number B has the right-hand side, but I mean, that's about a statement for any x. So maybe these properties imply that something has to be true for any space x.
Well, so this is an isomorphism between two complex vector spaces. And one of those complex vector spaces is this, which would be isomorphic to this, which would be isomorphic to this, which would be the complexification of this, which is exactly what that statement is. OK, so how do we fail to construct such a category? So let me tell you what sort of the obvious attempt would be to construct such a category. So the first...
The second isomorphism we said, that has an E of a point in it.
E of a point, yeah.
Well, why are those two isomorphic? The second isomorphism you said.
The second isomorphism.
The first one you said that mass is isomorphic to that.
Yes.
And then you said the one on the left, B left is isomorphic to C left.
B
Why is that?
B left is
I mean, that...
C left is C right. C left is A left. Tensor C.
These are the same. So if you believe B and C, you believe these are the same.
Right.
And then you're set.
Okay.
Right, so I said that E should be represented by a commutative ring spectrum. And what that means is that there's a good theory of E modules, meaning, so E is like a ring in the world of cohomology theories, and there's also a good notion of cohomology theories that are modules over E. So those can be organized into a category which I'm going to write as mod E. So here's sort of the obvious way that you would attempt to construct a category C with these properties. So let's take C to be the category of local systems on X with values in this mod E. So a family of cohomology theories parametrized by X, an object of C would be a family of cohomology theories parametrized by X, which is acted on by E. So then C satisfies A. So I should tell you what the unit object is. So the unit object is going to be the constant local system with taking the value E. And now, what happens if you make this definition if you compute HOMs in this category of local systems from the constant local system to itself? Well, what you recover is, when you set up the definitions correctly, just tautologically going to be the E cohomology of X. So A is OK if you make this definition. On the other hand, B is obviously not OK. So what happens if you compute C linear Homs from the complexification of this thing to itself? So here I'm imagining that I have some embedding of E of a point into the complex numbers, and that gives me some way of taking local systems of E modules and producing local systems of C modules. And then what am I going to get if I do this? Well, more or less the same reasoning is going to tell me that I'm going to get the cohomology of X with coefficients in the complex numbers. This complexification of 1 is just going to be the constant local system of C vector spaces given by C, or maybe some 2-periodic version thereof. But what you're going to get is not the cohomology of the n-fold loop space of X, it's the cohomology of X. So let's call this B prime, or let's call this not B. This is the failure of B. And then, well, if you believe the Hopkins-Kuhn-Ravenel theorem, then you must believe that C also fails if you make this definition. If this was isomorphic to this, well, you would be proving a much more naive statement of the Hopkins-Kuhn-Ravenel theorem, namely that the E cohomology of X tensored with C was the same thing as the complex cohomology of X. You'd be proving that changing cohomology theory was compatible, or tensoring with the complex numbers. It doesn't matter whether you do it before or after taking cohomology. So C also fails in this example. So the idea is Hopkins-Kuhn-Ravenel is supposed to be telling us that there's some better version of this category of local systems. There's some better version where B and C would be true. So we have, and the existence of such a category would imply the Hopkins-Kuhn-Ravenel theorem. So what I would like to do now is tell you about that modification.
I mean, is there a point that we haven't used the p-finiteness?
What's that?
I mean, we haven't used any assumption on E. For X.
Yeah, we haven't used any assumption on E, and I'm going to give a definition that's only really going to be a good idea when X is p-finite. Oh, I should mention, C fails when X is something like p-finite, but it always is true if X is a finite CW complex. So if X is a finite CW complex, this is always, the naive version of this statement is always true. So this is a very different notion of finiteness than requiring that you're made out of finitely many cells. Requiring homotopy groups to be finite is very different from requiring that you have finite homology, finitely generated homology. OK, so this construction doesn't work. So now I want to tell you the construction that does work, or at least a construction that's much closer to working. So first I want to make an observation. So let X be a space, and let L be a local system of E modules. On X. So I'm going to write gamma XL to mean the global sections of L. And this I mean to think of as an object in this world of E modules. This is another E module. But you can say more than that it's an E module. Because if you take, so this is an E module. You can think of it as a cohomology theory. And the cohomology groups of a point you can think of as the cohomology groups of X with coefficients in L. But if you have a local system of E modules on X, then the cohomology groups of X with coefficients in L, they're not just modules over the E cohomology of a point. They're modules over, you get modules over the E cohomology of X. So this is we can say something even better.
A local system of E modules means what?
A local system of E modules, well, it means if I think of turn X into an infinity category, it means a functor from that infinity category into mod E. So for every point of X, you supply an object of mod E. For every path in X, you supply an isomorphism between the corresponding objects in mod E. For every 2 simplex, you supply
what's an object of mod E?
An E module.
And what is that? What kind of abelian group is that?
It's a spectrum. It's a spectrum with an action of E.
What?
With an action of E, an E module spectrum.
Oh. Okay.
So in fact, we can say something a little bit better. So
in a local system, in the infinity sense, if you deform the path, what happens?
You get the homotopy between the maps. You get a homotopy between the maps. So you can say more than this. This is not just a module over E. This is a module over E of X. So I'm going to be sloppy in my notation. This was my notation for the E cohomology of X. But the E cohomology of X is actually pi 0 of a certain spectrum, which I'm also going to write as E of X. Or this is something that you might call E to the X. It's the spectrum of maps from X into E.
I don't have a good feeling for what a local system means, whether it's like a vibration or a locally flat vibration. Sort of
Locally
like a vibration, because when you deform the path, the map deforms.
I mean, so I can just...
Holonomy along a path changes when you change the path by
Yeah.
homotopy.
Yes.
Right? So that's like a normal vibration with a connection, isn't it?
Well, I mean, it changes by a homotopy, so that's a rigid thing. I mean, there's not... I don't know exactly what you're asking, but... I mean,
I'm asking, is it more like a bundle with connection?
it's like a bundle with flat connection.
I don't see why it's anything like a bundle with flat connection.
Well, it would be a bundle with flat connection if that was an ordinary category, but it's a higher category, which means there's a notion of homotopies between morphisms, and you have to allow those in the definition.
But see, any vibration, if you replace the fiber by the change in the fiber, becomes like a local system, because you can have this...
Absolutely. So any vibration determines a local... Any vibration from Y to X determines a local system of spaces on X. A local system on X with values in the infinity category of spaces.
Right.
So now I'm thinking about local systems with values in the infinity category of E modules.
So they're sort of like spectrum, but I mean sort of like vibrations of spectrum with this additional...
Yeah, it's like you have a vibration where the fibers are spectra.
And the structure group has E in it somehow.
OK, so now suppose you have a map of spaces from X to Y, and you have a local system L on Y. You can pull it back to get a local system on X. And there's a relationship between global sections of L and global sections of the pullback. Namely, any global section of L will determine for you a global section of the pullback. But we can say more, because this thing is a module over E of Y. And the target is a module over E of X. So in fact, you get a map from this tensor product into global sections of the pullback of L. And this is not necessarily an isomorphism. And that's in some sense exactly what we're worried about here. Because what are we saying? What happens when Y is a point, and X is the space we're interested in, and L is the local system given by the complex numbers? So then this left-hand side would be something like the E cohomology of X tensored over the E cohomology of a point with the complex numbers. And that's mapping to the right-hand side, which is like the cohomology of X with coefficients in the complex numbers. And this map we're expecting is not an isomorphism for the kind of spaces that we're interested in. So the failure of maps like this to be an isomorphism that's sort of why local systems are not quite the right thing that we want to consider. So what I'd like to do is modify this category of local systems by sort of building in the idea that this should be true. So let me make a definition for you. So definition, well, let me call this a twisted local system. On X is the following data. So A, for every map, every time you have a map from T to X, where T is a particularly simple space. So let's consider maps from T to X where T is a classifying space of a finite abelian P group. So every time you have such a map, let's call that map alpha, you're supposed to supply a local system, L alpha, of E modules on T. And this should be compatible with base change. So I want to say that if we have T prime, if we have a map alpha from T to X and another map beta from T prime to T, then what we should be able to do is, oh, sorry, not a local system. Sorry, this is not what I wanted to say. I wanted to say a module. Let me write it as L of alpha over E of T. And if we have a map T prime mapping into T, then we're supposed to be able to compute L of alpha composed with beta. This is just supposed to be obtained by taking L of alpha and tensoring that over the E cohomology of T with the E cohomology of T prime. So now, what would happen if you didn't have this problem up here? What would happen if taking cohomology always was compatible with pullback? Well, in that case, any ordinary local system on X would determine a datum like this. Namely, if you had an ordinary local system on X, you could define, and you had a map alpha from T into X, then you could define L of alpha to be global sections of the restriction of your local system to T. And if the kind of maps that you're considering up here were always isomorphisms, then you would have the data that B is requiring. So, but since this statement up here is not true for the kind of spaces we're interested in, this is sort of a different definition. So now what I want to say is that this category of twisted local systems satisfies conditions A, B, and C. But that's not quite accurate. So this is the definition. This is, let me say, the right definition after P completion. And there's a more complicated definition that you can give that is the right definition whether you P complete or not. And why don't I not say anything about that?
One has to understand B more in the way that is the functor from the, say, these t's over x, from the cutting of t's over x to the spectra?
Absolutely, yeah.
So it is more than...
Yeah, so there's a C which says some kind of associativity isomorphisms and dot, dot, dot. Yeah. OK, so let me tell you a little bit about this category of twisted local systems. So I need first to draw a picture. So I'm going to draw a picture for you of a scheme. That scheme is the spectrum of the E cohomology of a point. And I don't know how to draw this picture, but remember what the E0 of a point looks like. This just looks like a power series ring on n-1 parameters over the p-adic integers. So the spectrum just means the set of all prime ideals in that commutative ring. And there's a particularly interesting prime ideal here, namely the maximal ideal generated by p and v1 through vn-1. So that's this point that I was trying to indicate here. There's another prime ideal. This is an integral domain. So it has the ideal 0 is prime. That's some generic point for this scheme. Maybe I should try and draw that kind of like that. There's a big fat point here. And there's another picture that I want, something I want to add to the picture, which is spec of E0 of the classifying space BZ mod P. So remember, Morava E-theory, one of the things that I said characterizes it is that this ring is just a finite module over this ring, a finite free module of rank p to the n. So you should think about this map. It's something with finite fibers. Generically, a fiber has p to the n elements, though at certain special points it might have fewer fibers. The fibers might be smaller. So for example, over this special point, there's only one inverse image. So I'm making assertions here, but these are assertions that you can just see directly in the example that I started with. So let's do the n equals 1 example. N equals 1, so then E0 of a point, so this is p-adically completed K-theory. So E0 of a point is the p-adic integers. And what a spec of the p-adic integers looks like, well, there's exactly 2 primes, namely the big fat one and the little one. So I don't know, maybe you should draw it like this, but maybe you should draw this point as, I don't know what the best way to draw this is. It's got a closed point and an open point. And now what does E0 of Z mod P, BZ mod PZ look like? Well, this is, after p-adic completion, the representation ring of Z mod P. So Z mod P has a canonical representation where the generator acts by your favorite pth root of unity, and all the other irreducible representations are just powers of that, and all representations are linear combinations of those irreducible representations. So this thing as a ring looks like ZP adjoin T, if T is your favorite irreducible, modulo T to the P minus 1. So what do you get when you take spec of ZP brackets T mod T to the P minus 1? Well, I want to say you should think of, let's draw spec of ZP as some kind of a line with a special point here. But you should think that line is sort of really a small infinitesimal neighborhood of this point. And now, what does this look like? Well, generically, if you're in characteristic 0, there are p different pth roots of unity. So there are p fibers over the generic point. But if you're in characteristic p, then there's only one pth root of unity. So over this special point where you set p equals 0, the inverse image has cardinality 1. OK, so this is a little picture. And this picture is important for understanding the structure of this category. Well, So the collection of twisted local systems on X can be organized into a category, or really an infinity category. I'll just say a category. Let me write it as loc X, but I'll write a little tilde to remind you that it's twisted. And this category is linear over this ring. It's linear over E0 of, well, it's really linear over the ring spectrum E. But, which means you should sort of think of this category as spread out over this spec E0 of a point. And in particular, you can take this category. There are algebraic constructions that implement the idea of sort of taking this category and seeing what it looks like at a point of this space. So let's pick your favorite point P in this space. P is a bad name for a point. Take your favorite point, little x. And let's give a name to this map. Let's call that phi. So if you look at the inverse image of x, and now I just mean its inverse image as a set. Well, I mean, for algebraic geometers, I mean the geometric fiber over this point. This is going to be a finite dimensional vector space over Fp, or the ring Z mod P. It's a finite dimensional vector space whose dimension can range from 0 to n. And that'll sort of depend on how generic this point x is. If x is the special point corresponding to the maximal ideal, this vector space has dimension 0. If x is the generic point, this vector space will have dimension n. So finite dimensional vector space over Zp, let's say of dimension, let's give a name to that dimension, d of x. So now I'm going to assert something about this category. So let me say, very informally, locally at the point x, this category of local systems, twisted local systems, what does it look like? Well, it looks like the category of untwisted local systems. I defined those for you earlier, although I didn't introduce this notation for it. It looks like the category of ordinary local systems, but not on the space X, but on the space of maps from an m-dimensional torus into X. So what do I mean when I say locally at this point X? Well, what I mean is you have to, in some sense, X corresponds to a prime ideal in this ring. What you have to do is first enlarge the coefficient ring a lot, and then you have to complete with respect to that ideal, some mixture of the two procedures. So this is something that should be familiar in the K-theory case, because if you write down that isomorphism between the representation, the complexified representation ring of a finite group and the ring of class functions, you have to work over the complex numbers. You can't just work over the rational numbers. The character of a representation of a finite group doesn't usually take rational values. You have to enlarge Q at least somewhat. You don't have to go all the way to the complex numbers, but it's enough, say, to take Q and add in all the roots of unity. So by locally at this point, I mean you have to do something analogous here. You have to do something that's kind of like taking this ring and adding lots of roots of unity. And you also have to complete with respect to the prime ideal corresponding to this x. But once you do those things, then this category of twisted local systems just looks a lot like the category of ordinary local systems, but with respect to a certain loop space. And I want to say now, this proves, if you believe this, this proves A and B. Because, well, A is a calculation that you do when you're completed at this central point, and B involves a calculation that you do when you're completed with respect to this generic point.
Now, 1 sub c means what?
So 1 sub c means, so 1 is the, well, I want to say 1 is the constant local system with value e. But in terms of this definition, what do you want to write down? Well, One is the twisted local system that assigns to every map alpha from t into x e of t as a module over itself. And it's clear that if you take e of t and tensor it over e of t with e of t prime, you just get e of t prime. So it's sort of the obvious thing that you can write down there. And then what does it mean to tensor it with the complex numbers? Well, roughly just take what I just said and tensor it all with the complex numbers. That's not quite right, because as I told you, my definition of this category is not quite right. This is only correct after p-adic completion, so to really answer that question, I would have to give more details. So yeah, you choose an embedding of E0 of a point into the complex numbers in order to do this. All right, so now what about C? Well, that's where the real theorem is. So now I've given you a definition, and now I want to say something interesting about it. So this is where my lecture is going to dovetail with what I was talking about last week. So let's suppose that you have a map f from x to y of spaces. So you can talk about local systems on x and twisted local systems on x. So that's a category which is defined over there on that board. You can talk about local systems on y. And there's a sort of obvious way that you can take a local system on x and, or sorry, local system on y and pull it back to get a local system on x. So let me state this as a theorem. So the thing that I've made a definition, and I claim this definition is much better behaved than it has any right to be. And this theorem is what's going to articulate that. So this theorem, well, one way of saying it is that the functor f upper star has left and right adjoints. So let me call those f lower shriek and f lower star. But now, having introduced a notation for them, I don't need two different notations because they are canonically isomorphic. So you should think about f lower shriek as some sort of procedure of taking homology along the fibers of this map from x to y. And f lower star is some sort of procedure of taking cohomology along the fibers of x mapping to y. And so this is a sort of very unexpected thing. It's saying homology and cohomology give you the same answer. And for those of you who attended my lectures last week, the construction of this isomorphism is exactly the construction that I described last week. It's an iterative construction involving some kind of norm maps. You just, instead of talking about ordinary local systems, you introduce this category of twisted local systems. So this has a lot of consequences. So one consequence is that something like C is true. So another way that you can think about this isomorphism described in C is saying that if you look at the map from x to a point, well, what's the right-hand side here? The right-hand side is what you get if you take the constant local system, let me call it 1, and you first complexify it, or first tensor that local system with the complex numbers to get another local system on x, and then push it forward to a point. In other words, take its cohomology. And the left-hand side, well, the left-hand side is what you would get if you first took the cohomology of the constant local system and then tensored that with C. So C is, condition C over there is saying that you can first take cohomology and then tensor, or first tensor and then take cohomology. And that's something that you don't generally expect cohomology to satisfy. In fact, if you, by cohomology, you literally mean cohomology of a local system, it's not true. And that's exactly the point of this whole discussion. But if you replace this notion of local system, if you modify it in this way, then it is true. And the reason is, well, tensoring with the complex numbers, that's a special case of a colimit. You could write the complex numbers as a colimit of finitely generated E modules. And in the finitely generated case, there's no problem. The whole problem is whether or not, when you take the colimit, that commutes with taking cohomology. Usually, you don't expect that to be true, but taking colimits does commute with taking homology. And if homology and cohomology are the same, then there's going to be no problem. So I think now I'm out of time. But let me just conclude. I promised you at the beginning that I would somehow connect this to topological field theories. So let me just conclude by indicating that this theorem powers for you the construction of a topological field theory. So let me be a little bit more specific about that. So let E and X be as before. Then one can build a once extended topological quantum field theory, which I'll call Z. So this is going to be defined on n-2, n-1, and n manifolds. That's what I mean by once extended. And here's the formula for what you're supposed to do to a manifold of dimension n-2. If you have a manifold of dimension n-2, you're going to assign to that a category. And what you're going to assign is the category of twisted local systems on the space of maps from M into X. So what I'm describing now is going to be some version of Dijkgraaf-Witten theory. So Dijkgraaf-Witten theory I talked about last week, that's what you would get if you were working over the complex numbers and you took X to be the space BG, where G is a finite group. So to an n-2 manifold, you assign the category of local systems on the moduli space of G bundles on X. Well, if you want to work not over the complex numbers, you better put this tilde on the notion of local system in order for this to be well behaved. And well, why don't I just conclude by saying, what do you do, very quickly, what do you do if you have a Bordism? So B, if this is an n-1 manifold, which is a Bordism from an n-2 manifold M to an n-2 manifold N, well, you can consider maps from B into X. And a map from B into X restricts to give you a map from M into X or a map from M into N into X. And now to this, you're supposed to assign a construction which takes a twisted local system on this mapping space and makes a twisted local system on this mapping space. And that construction is just take your local system, pull it back, and push it forward. Now, in order for this to, that's a definition that you could always give. You don't need any theorems to power this definition. But the point is that the theorem that I'm telling you enables you to define this as a topological field theory that's also defined on n manifolds. N is the interesting number because when you evaluate this on an n manifold, what you get is something that's like a number, that's like a numerical invariant of your manifold. So, well, in order to make that construction, I won't say any more about it, but it's very important, as I explained last week, that these two functors be the same. All right, I think I will stop there. Thank you.
Any questions, comments?
So I think you said that you get A and B by restricting to the close point and the generic point?
Uh-huh.
Do you get something interesting? I mean, you could consider other points.
Yeah, you do. Well, all right, so there's something I really should have mentioned that I didn't, which is the proper context for this whole construction. So what do you need in order to construct this category of twisted local systems? The definition is still here. So you want to give a definition like this. And what you need is for every time you have a finite abelian P group, you need some candidate for the ring that's going to play the role of the E cohomology of T. Now, this can be interesting in situations where that ring is not actually given by taking the cohomology of T with respect to any cohomology theory. So let me give you an example of an analogous construction. So what if you didn't want to recover p-adically completed K-theory, but you just wanted, what if you didn't want to recover the character theory of finite groups after p-adic completion, but you didn't want to p-adically complete? Well, if you don't p-adically complete, the representation ring of G is not isomorphic to the K-theory of BG, but instead, what goes there is the G-equivariant K-theory of a point. And now you can consider a construction which, if T is the classifying space of a finite abelian P group, space BG, where G is a finite abelian P group, then you can consider the construction which takes that to the representation ring of the group G. Well, I shouldn't really write the representation ring of G. What I should really write is the G-equivariant K-theory of a point. I'm going to think about that not as a commutative ring, but as a ring spectrum. So that, if you use that as a replacement for E of T in this, then you get a reasonable definition which will reproduce for you, let's say, the statement that I started with, but before you p-adically complete, where you don't have to mention p-adic completion. So that's not a very convincing argument that you should allow this more general definition. But let me give you, say, the real place where you want to think about that, which is in the context of elliptic cohomology. So in the world of elliptic cohomology, there's a moduli stack of elliptic curves, and over that there's a family, universal family of elliptic curves. And what you can do if you have the classifying space of a finite group G is consider the thing that classifies maps from the Pontryagin dual of G into the elliptic curve here, into this elliptic curve. So that's a finite flat group scheme over the moduli stack of elliptic curves, or a finite flat map to the moduli stack of elliptic curves. And the push forward of the structure sheaf on top is a candidate for something that you can replace E of T by in this context. And if you make that replacement, what you arrive at through this definition is, well, it's something that knows about equivariant elliptic cohomology. It's what you might regard as a categorification of equivariant elliptic cohomology. It's a category in which the equivariant elliptic cohomology groups can be interpreted as HOMs. So I'm not sure how much sense what I just explained made. Why don't I stop and ask if there are more questions?